having fewer of those partitions, for one, the multi-grid seems to work a lot better. So that's one of the things I showed in the main pull request for this work, which is number 861, is that you get faster convergence when you use multi-grid by decomposing the domain, by not decomposing the domain so much. And in some cases, that's the difference between being able to converge the case or not being able to converge it at all. So this example here with 96 MPI processes, it would not be possible to converge the case, but with 16 MPI processes, each one then unfolding or multiplexing into 6 threads, which gives you the same total 96 scores, the convergence is much better. Then there are other algorithms, for example, to compute wall distances. This is one of the things that was brought up in the last developers meeting. To compute wall distances, you need to collect the boundary information and send that boundary information to every MPI rank. Which, if you have a very large problem, this can give you some problems with memory. So this is of course a problem if you have millions and millions and millions of cells. There are other parts of the code that work better with the hybrid approach. For example, when in multiphysics cases where you have interpolation between different zones, that again usually requires you to collect all the boundary data on each MPI rank, and that again is something that can give you problems if you have a large scale problem, and if you're trying to scale it over a lot of nodes. So those are the pros of using this hybrid approach. The cons is that basically the main one is that you have an extra layer that you need to think of. So with MPI, you just need to call the communication routines from time to time to refresh the data that you have in the halo cells. With the hybrid approach, you need to think that you also need to think how you distribute the work over the various threads that you create, and so on. So for those that don't know OpenMP is a very well-known API to do threading in kind of a easy way. So it works based on pragmas. So you put some pragmas to create a section of code where you have multiple threads working on it simultaneously, and then you have work sharing construct to then divide a certain region of work, for example, a for loop, to divide that for loop over the different threads. So there's because this is based on pragmas, the way to encapsulate this functionality and to be able to turn it on and off when we compile the code compile the code with or without this functionality is a bit of a preprocessor, involves a bit of preprocessor trickery. So this is all defined in this header OMP structure, and this has a bit of basically all the SU2 OpenMP pragmas are defined based on this master macro, and this is something that we disable with some preprocessor trickery if we don't want to use OpenMP. And then using that master macro, we define all the other constructs that are used. So how is this used in the code? Broadly speaking, some things are very easy and very natural to do, and I'll give an example of those, and I'll give an example of things that are not so simple or so straightforward to do. So the easiest thing you can think of is matrix multiplication, or at least row major matrix vector multiplication. So this is the matrix vector product function of the system matrix class. It's just a loop. It's just a loop over all the rows of the matrix, and for each row, well, you do what you already know. It's a dot product. It's a sparse dot product in this case of the row of that matrix with the vector, and that gives you the result of the multiplication. And so here it's very natural to call this method with inside a parallel region of the code, and then we just divide the work over the threads that arrive at this function. So when different threads get to this function, they know that they will, each of them will work on a certain number of rows of this loop, and then once it finishes, it asks the OpenMP runtime for another chunk of work, and so on and so forth until they all execute this loop in parallel. What this gives you, which is another advantage of this approach, is some automatic load balancing. So this work is this total amount of work over from 0 to endpoint domain is being dynamically scheduled as it's being done. And so that means that you can also expect some better strong scaling from this approach. So if you have if you imagine that you have if you're trying to parallelize things very heavily, if you're trying to have each core working on say 10,000 or even fewer nodes, then having some dynamic load balancing will give you better scaling, because the partitioning that we do for MPI, it's static, and that I know of, it doesn't attempt to balance things based on how much work each subdomain will have. And you can imagine that some subdomains will have more boundaries of a certain type than others. Others will not have any boundaries at all. And so there's a natural work in balance when you just divide things kind of geometrically like this. Then there are certain things that we cannot parallelize at the moment. So for example, all the communication strategy, because we still need MPI communication. It's you guys can still hear me, right?
Yep.
Yeah.
Good.
Sorry, I'm not. This thing of not having feedback from the audience is tough. Okay, so for those things that that cannot be done in parallel by multiple threads, what we usually have is this kind of construct where you have master, and this is equivalent to our if rank equal master node. So only the master thread performs these communications. Okay, and then usually after a region of code where only one thread did the work, and we need the other threads to know the results of that work, we need to add a barrier. And with this OpenMP implementation, you see a lot more explicit barriers than you see with just MPI. So with just MPI, you don't really see calls, or we don't have a lot of calls to MPI barrier, but they are somewhat implicit in the communications we do. It's similar with OpenMP. You just have to call this barrier function explicitly a lot more times. So for example, here we call it after the master thread does the communication, so that all the other threads have the same view of the result of this multiplication, and we need to call it just before we start the multiplication to make sure that all the threads have the same view of the vector that it's being that's being multiplied, that the matrix is being multiplied by. Okay, so that's actually not the simpler example. The simpler example is if you have just a sum of two arrays or an assignment of two arrays. Then you don't have any communications, and it's a lot more straightforward. Where things get trickier is where you need to reduce the results across multiple threads, because now for something like a dot product, now you have to reduce the sum over all the threads, and then we still have the MPI layer, so you have to reduce it again over all the ranks, over all the MPI ranks, and so that looks something like this. So the dot product is called in parallel. We have a member variable of this class that we use as a temporary. This is a member variable of the class because this is the only way to, well, this is one of the ways to make this variable known to all the threads. So for example, when we create a local variable here and we call this in parallel, there will be n of these variables, so one per thread. So if you want something that allows you that all the threads can see and access and manipulate, then it needs to be either a member of the class that was created before the threads were created, or it needs to be a static variable. So what we do here is, again, very simple, very simply, we compute a partial dot product for each thread. So that's done here. This will divide the work over the threads. Each thread will have a result, a partial result. Then we need to reduce that, and we do this with in this case, we can do an atomic addition. So we add this partial sum to the dot result, and then we need to reduce this over all the MPI ranks. And so again, you need a barrier. You need the communication to be done only by the master, and then you need a barrier again to make sure that the result is now consistent across all the threads. So that's as simple and as ugly as it gets. If you want to do other types of reductions, for example, minimum and maximum, it's exactly the same. It's exactly the same process. You need to first compute a local reduction to the thread, then a local reduction over inside the particular MPI rank, and finally one over all the ranks. So you can imagine a tree-like structure where first you branch out for the ranks and then you branch out for the threads. So what you can absolutely not do, and what you need to be very careful with, is data races. So if for example here these threads were trying to write simultaneously to this variable that is shared to them, that would just give you garbage results. So if you have multiple threads writing to the same location in memory, that's just going to be a disaster, basically. So for example, we need to do things like having one numerics object for each thread to work on. So when we discretize, when we compute convective fluxes, for example, we have one convective numerics class for each thread to work with. And that's because in using this numerics class, we need to write into that object all the pointers and so on that it will need to then pull the variables into its computation, and that it's handled by having one per thread, basically, which is, in essence, it's not different from having from the MPI implementation, except here this is managed explicitly. You need to create them, and you need to manage the objects like this. The other area where data races could happen is then when you take the results of the numerics class and you want to write and you want to update the residual and the Jacobian. So what we usually do is we add to the residual on one side and we subtract from the other, and very similar for the Jacobian. The Jacobian update needs to update 4 locations of the matrix: ij, ji, ii, and jj. So 2 diagonal entries and 2 off diagonal entries. In writing to this residual, you can imagine that you have multiple threads processing different edges. There is no guarantee that if you have intersecting edges you being worked on at the same time, you would get a data race as 2 threads try to update the same I point or the same J point. And similarly for the diagonal updates of the Jacobian. So what the alternatives we have here is one, we can have grid coloring. So we have a number of colors, and colors are essentially sets of edge indices that we have created in a way that there are no intersections. So we group all the edges in subgroups called colors, and within each of those colors, threads can work in parallel freely, knowing that the data is organized in a way that prevents this race conditions, this concurrent accesses. The other way we can, so grid coloring is a difficult thing to do, especially for unstructured meshes where you can imagine that you have a lot of hedges. If you just have tetrahedrals, you have a lot of hedges connecting to every single node. So grid coloring gets tricky to do in those conditions, and actually with the simple algorithm that I implemented, it very often just fails or requires too many colors. And so the other thing we can do is have kind of a reducer approach. So what we do is instead of writing to the residual as we compute, we instead are storing the fluxes for each edge as we go along, and you can see here there's no chance of having race conditions here. Each edge is its own independent thing. Again, for the Jacobian, we don't set the diagonals. We only set the off diagonal entries, which are unique form a unique pair for each edge. And then once we finish the loop over the entire loop over the edges, we do a reduction. So we then sum for each cell or for each node, we sum the fluxes of the edges that connect to it. And similarly for the Jacobian, we set the diagonal of the diagonal entries as the sum of the respective column, which is completely equivalent mathematically to this. You just need to split the process in 2 steps. So that's what is done when grid coloring fails. So yeah, that's I think we're pretty close to an hour, so I think I'll stop here.
Pedro?
Yeah.
Can I ask on that last point, so the excuse me, the differences between grid coloring and using the reduction strategy. So what's the difference in terms of performance? Have you looked at that at all?
Actually, for my cases, this reducer strategy seems to work a lot better than coloring.
Yeah, I recall we went for something closer to the reduction strategy in the previous work some years back, but I don't remember what the performance head-to-head was, so I'm interested. Yeah.
Okay, interesting. Yeah, and it seems to work better. So in the initial benchmarking or prototyping that I did in the issue 789. I made a mock-up implementation of a dummy numerics class that would write to the residual and matrix and so on, and this separation was actually slower. Slower than the grid coloring, but that was grid coloring with edge groups. So not coloring each edge individually, but coloring actually groups of edges as an entity. Yeah. Because if we color just one edge, if we give one color to each edge, then the performance is quite low because it just destroys the spatial locality.
Right.
Okay.
Yeah, I think one thing we had done before was use metis to go ahead and partition, like do a second level partitioning using metis to assign a color to a group of edges. So was it something like that that you tried?
No, I just implemented greedy coloring and
just over groups.
And yeah.
Okay, got it.
So a lot of that functionality is in this header file. Toolboxes and graph toolbox.
Structure?
No, that's something else. That's I think that's something that Edwin did for the FE solver.
Oh, right. Yep.
So there is a very simple. Yeah, there is a very simple grid coloring function here.
Sounds good.
Yeah. What's the question?
I have a practical question actually, referring to this graph that you just showed for the convergence graph, Pedro. Maybe I missed that, but does it require from any input from the user to decide on the distribution?
So the way it's done is so when the code starts, initially it takes a default number of threads from the environment. So usually, what will be defined for a computer is the maximum hardware threads that it has available. And so that if you don't specify anything when you call SU2, that's what it will try to use per MPI rank. If you want to fine tune it, there's this command line option with just -t or -- threads, and you specify the number of threads per rank like that.
Okay. So you can still tweak per case.
Yeah.
Okay, clear.
Could it be that people might accidentally run with OpenMP here? So if it finds that it built with OpenMP and they have the environment variable set, or they ask OpenMP get max threads, could it be that people run with OpenMP without being aware of it, or is the default to 1 thread per rank?
Oh, I mean, right now, if you don't compile the code with OpenMP, there's absolutely no change. I've implemented this in a way that well, hopefully I did, or I looked at some assembly, and I think it works. If you don't compile with OpenMP, then it's the old code, verbatim.
Yeah, I guess
all that
maybe
functionality goes away.
Another way of asking it is you have to actively request OpenMP in the Mason build, right?
Yeah. So you
Okay.
need -d with -omp equal true. I think I've updated the documentation. I think
Great.
I think that's explained
And
there.
then one last question. So what's the current status for kind of the breadth by the OpenMP framework?
Yes, I had that open. So right now, what is covered is the turbulent solvers, the compressible flow solvers, and the structural solver. So what's left to do is, well, the continuous adjoint solvers are not covered. The incompressible is also not covered, and the heat solver is not covered yet. Okay. But nothing breaks. Nothing breaks if you compile the code with OpenMP and use one of those solvers. It will just not be parallel. So right now the threads are started at the level of the integration. So for example, the entire multi-grid iteration, we start the threads here only if the solver declares that it has support for this, and yeah, that's it. The threads are started here. So for the default of this function is false, and so if it's not implemented, then it's business as usual and nothing breaks. So all the functions in system matrix or the linear solvers, they are safe to call in parallel, but they can be called sequentially as well, and they work just fine.
Okay, sounds good.
And if you don't compile the code with OpenMP, all these macros are empty basically. They just become an empty string, and so there's no downside. There's no catch if you don't compile with OpenMP.
Yep. Thanks.
Okay. Thanks, Pedro. Very nice overview. I would actually suggest that we keep the meetings like really to more or less an hour, if everyone agrees with that. But therefore, we have it like in a weekly manner. So in the agenda there were like more topics, but we will then probably cover them next week, I would say, because yeah, I think it makes sense. Or is there someone that disagrees? Probably not, I guess, because of my authority. Yeah, so like I said, it will be recorded every week, and let's see how that works. And yeah, so are there any other questions? Apparently not.
I mean,
Well,
if we is there? I guess it depends on Giant. If I'm quite interested to hear about the shape optimization.
Yeah, I mean this is a question now, right? If we want to have it like longer than 1 hour or not, this is just a general thing. I mean, we can also, I don't know. I don't know, it depends on the people. I mean, if people are interested to do that now, then we can also do that now.
Ideally, we keep it to an hour in general, because otherwise it ends up messing with other things. But if people want to hear about it now, I don't have any slides prepared, but we can talk about it in general.
I don't know what the best approach would be.
Well, is there anything that's holding people up, or sort of a blocker for people right now that would be worth discussing in a minute or two, or should we just wait? I'm kind of in favor of keeping it to an hour as well, but that's just me.
I mean, we can maybe have a pre-discussion for next week, essentially, for the people who are involved with that. And then we just present already the first ideas that we had. I think that makes more sense than, yeah, having like all of the others. I mean, everybody who's interested can, of course, stay and listen, but I would say that we do it like that.
Yeah, sounds good to me. So adjourn unless you want to stay and listen for this part, and meet next week. Yeah.
Yeah, that's what I would say. So if people want to stay, they're very welcome. Otherwise, we will give like a rough overview probably also next week on what we talk. And it is also recorded in case people want to see it. So yeah. So people who are interested stay, and the others can leave.
And we'll have a proper discussion about it in the next meeting as well. Right?
Yeah, exactly. So we maybe create some rough ideas already. Maybe we have a summary then next week that or something like that. I don't know. Yeah.
Yeah, that sounds good.
Okay.
And maybe a short thing I will leave, but for the agenda, can we keep somewhere like a dynamic list?
Yeah, I would say the link that I
topics?
sent out there, we can just have that and just edit the document.
So that would be nice to maybe define like the next several weeks topics.
Yeah, I mean, feel free to add topics there.
Okay.
I will remove the topics that we already discussed then.
Okay. And the link to the YouTube, we will publish it somewhere.
Yes, I will publish it somewhere. Yes.
Okay.
I just have to see how that worked out and whether it worked this time. Next week it will be better.
Okay. Thanks.
Yeah, feel free to crop the time I spent trying to get screen sharing.
Actually, I started the recording a little bit too late. So no worries on that.
I know, I'm sorry.
Okay, then I would say we have like a discussion on the. So everybody who wants to leave, feel free. I mean, we will record that, and it will be continued or started again next week. Okay. I prepared a couple of ideas that I had so far based on discussions with that I had with people already, because the shape optimization, the optimization framework is really like a thing that like bothers a lot of people at the moment. And you can see it also that we have like a lot of issues on GitHub regarding that. It's a hot topic. We should deal with that somehow. So let me just share my screen for a minute. There. Okay. So why do we need a rework of the optimization framework? Well, you probably know all the drawbacks that the current framework has. So first of all, it's not very flexible, and it's hard-coded for aerodynamic shape optimization problems. Then you see from all the issues and all the things that like you hear that it's very hard to keep like the Python framework up to date with the changes in the C++ code. So like a lot of changes that I did for the output, for example, are not 100% reflected in the Python framework because it's very hard to do that. Furthermore, it's inefficient, error prone because it has to handle like a lot of files and file pointers and things like that. Then it does not make use of all the capabilities that we have for the agent solver. So the agent solver is really flexible in terms of what we want to differentiate and what the objective function is and stuff like that. But the Python framework is not aware of that, and it's so rigid that it cannot really be used for advanced stuff. The optimizer cannot easily be replaced. I think a lot of people already played around with other optimizers, but it's not very easy to integrate them in the current structure. And then, the structure of the Python code is just very complicated. It has so many different levels, and it's hard to just click through the code and figure out what it is actually doing when you just want to evaluate like a simple objective function. So I think everybody knows what I'm talking about. So this is just from Giant. I took it from your pull request. So if you want to talk about these points, so it's just a copy from your points there.
So this was all of this was motivated from internship I had over last summer. I was trying to do shape optimization, even though the Python this shape optimization framework was made for aerodynamic optimizations. I still had a lot of trouble in like Tim mentioned, bringing any flexibility into the situation. The handling of large numbers of files is it's annoying, but it is something that needs to be done for now. Once we move into an in-memory Python, using the in-memory Python wrappers, then hopefully we can get rid of some of these file IO issues that we have. And the idea is also to try and make this as robust as possible. Adding new design variables, constraints, objectives is really difficult, and Tim has a very flexible way of doing that for the outputs. So being able to port that into the shape optimization framework would be really, really nice. And these are just some of the ideas that came out of that. So SU2 Geo is it's just a wrapper C++ function that calls a bunch of different geometry functions and the like, which can probably be all done in Python, and we can get rid of a module that way. And I know there's like SU2 mesh that's also not really being used anymore, which needs to be, so we can basically trim some fat with this as well. So adding a generalized thickness constraint, this is just a specific thing that I'm trying to do to try and evaluate thicknesses of any sort of geometry that's closed. Be able to do different types of geometry evaluation at the same time. Right now, you can only specify wing or fuselage. You can't do wing and fuselage. So being able to do some of the stuff like that, and these are sort of examples of more generalized things that we could potentially do. And also, like, all of the geometry evaluation currently is everything is just for aircrafts. It's you either do a wing, fuselage, or a nacelle geometry evaluation, and I'm sure people are using SU2 or hoping to use SU2 for more than just that. So having general geometry information would also be a way to evaluate general geometry information would also be nice. For example, like area of an inlet or something of that sort. Those are easy functions that can be put in place in a robust way. And expose some of the mesh deformation functions, and I know Tim also agreed with it. Like all of FFD should just be moved into a separate area of the code because it is so independent from everything else. And
yeah, I thought about making it like a separate library actually.
Yeah,
because it really not needs like all the things we have implemented in SU2 so far. Actually, it just needs for at least the FFD part just needs a point cloud. Right?
Yeah, exactly.
That's all it needs. Other functions, other parameterizations might need maybe a little bit more stuff, but even something like a Higgs-Henne function is totally independent of the connectivity and stuff like that. So even that is not, even for that it's not needed. So that would be great.
Yeah, exactly. And so a lot of this was also motivated by I was working alongside some people from University of Michigan, and they have a very robust optimizer and shape optimizer in a framework that sort of plugs into SUMB that they use as their solver. Well, I guess SUMB plugs into their shape optimization base, and then all of their FFD definition is just working with a point cloud, and it will make it very easy to define new design variables that are based on FFD deformations.
Yeah, exactly. That would be cool.
Yeah. One thing that if anyone has used the shape optimization, is that if a solution diverges, it just breaks and there's nothing we can do about it. So hopefully we can try and I want to try and find a way to intelligently handle these divergences, whether it's specifying a bad function evaluation if it diverges. So for example, like if you're trying to optimize drag and the solution diverges, just set a large drag value so that the optimizer still sees something but knows that it's not a good part of the design space to be exploring and can explore somewhere else.
I think that some optimizers can even handle like something like that. You can tell them, okay, this is a bad evaluation or something like that, as far as I can remember.
I was looking for that. I couldn't find that for SLSQP, or at least in the site kit.
No, not there. It was some other optimizer, I think, but I cannot remember which one it was. But
yeah, but we can take some of those learnings from other and maybe try and, because I know in general we've had best success with SLSQP and SNOpt, even though SNOpt isn't integrated since it requires a license. Those are the ones that are most commonly used for CFD-based design optimizations, if I'm not mistaken. But again, we can always play around with different optimizers, and if we can make this robust enough that it can just handle any optimizer, then that
should be the goal. Yes.
Yeah, that would really be the goal. Yeah. And something that one of the issues that just sprang up again was the multitude of shape optimization tuning parameters. Just because there's just so many ways to scale, like the design variables, the objectives, but not the constraints, or like the gradients of the objectives, but not the objectives themselves.
Yeah.
And it does, yes, it's very flexible in that you can specify a bunch of parameters and get exactly what you want. But ideally, we would want to try and make that invisible to a user and do some of that scaling behind the black box of the optimization framework, ideally.
Yeah.
Are all those scalings mathematically correct, or are they numerical tricks? So, for example, you scale down the gradient to maybe lead to not so aggressive line searches.
So I think it's consistent in that anything that gets scaled across the board, where as in it gets scaled and then gets scaled back when you're talking to the person, or well, I guess it's consistent, but it's not necessarily might not be mathematically sound.
Okay. I've been playing around with, so I don't use the shape optimization because I didn't start with shape optimization. I started with topology optimization, and I couldn't do any of that in in SU2. So I made a framework from scratch, and lately I've been playing with these strategies of saving the optimization if things fail and so on that you were mentioning, and these simple strategies of setting a large value or setting an infeasible value, they save you from a bad evaluation or a very aggressive line search. But if the optimizer for some reason really wants to go in that direction because the gradient points that way, let's say, but the mesh you get when you deform it to that position is just not good enough for the flow solver to converge, the optimization will still fail, because the optimizer will still be trying to push in that direction, trying to get arbitrarily close to a barrier function. I mean, they give some robustness, but it's not a silver bullet, let's say.
Yeah. Okay. Yeah. Are there some other questions on these topics? Because I just have some slides with just some ideas. Yeah, what we essentially have to do. Yeah, so we were always talking about the in-memory Python wrapper, right? This is the solution that we want to go for, and I think that everybody agrees that this is a good idea, I think. So we want to expose a lot of things from C++, even more than we have right now, to Python, but just some very high-level functions to run the code, to get some output, to run the H1 solver, to get the sensitivity and stuff like that. And it should be, I think, in a rather opaque manner. So that means the Python code should not need to know about the kind of objective function, for example, right? Because at the moment, everything in the Python framework depends on what objective function we use, and then the files are named like that, and those Python framework has to know all of that. But we want to get rid of that, I think. Yeah. So I think that everybody agrees that this is the way to go, right?
Yeah,
and there's some other comments.
Yeah, I think that's true, and then exposing more and more of the C++ would also make it easier for it to run SU2 through Python, which would make it a little more user-friendly, I think.
Yeah, exactly. Also to define some interfaces to embed parts of our framework into some other chains, whatever you want to think about, for DOE or whatever. Yeah, so that would be the way to go. And I mean, this is just some quick drawing that I did, because I was thinking on what kind of things we have to expose as an object in Python. So this is just a usual like chain of for optimization, right? So we have the surface mesh deformation, we have the objective function evaluation, objective function gradient, and then at the end we have the surface mesh operation for the gradient. So the first thing is, at the moment, the first step is what Dev is doing at the moment, and the last one is what Dot is doing at the moment. But I wrote that these are optional because we don't want to have it like only for shape optimization stuff. So we can also optimize like for other design variables. That would be also the goal. So I thought, okay, I mean, they just write there what structures we actually need. Yeah, it's not very detailed, but it helps a little bit to see what we have to do. So I mean, it's very easy, right? So the surface mesh deformation needs geometry structure, and that's it. Objective function evaluation needs the geometry and gives us a new solver where the solution is stored. So objective function gradient gets like a geometry structure and gets a solver structure, which is like the direct solver, and gives us a new solver structure which contains like the solution, or some object that contains the solution. And then yeah, surface mesh projection is the same. We give it geometry structure, solver structure for the surface sensitivity, and we get the final gradient. And then at the end, we also need a config structure, right? Possibly for all of these steps there. Yeah, so this is just what I was thinking about on how to actually do that. So that means we have to expose all these things to Python as objects. That's something that everybody agrees to. Do we need that?
I'm for it. If it's possible, I would.
Yeah.
To have
so there's the last two steps is where I would have some questions, because in our current workflow, or the few times I used it, when we create a new design point or optimization iteration, we deform the mesh of the previous iteration, right? We don't deform always the
it's always the initial mesh that is deformed at the moment.
Yeah, it's always the initial.
It's always the initial.
Yeah,
Okay.
it's not incremental.
Okay, because when we compute, when we do the projection with Dot, we are building the stiffness matrix based on the current coordinates of the grid, right? So the deformed coordinates. But when we do the deformation, we compute that matrix based on the initial. So there's an inconsistency. There's kind of an inconsistency.
I'm just thinking where it gets the mesh from.
Well, it gets whatever you give it, and but you need to give it the one with the FFD in the correct position.
I'm just thinking whether the mesh deformation, so the def has in this directly, whether there's a link to the original mesh always. Yeah, must be, right?
There's a link to the original mesh.
Yeah, okay. Yeah, but I've never thought about that. Okay, yeah, you're right. Then for Dot, we don't do that. We use the current one, yes.
It's not a big deal. I mean, depending on the magnitude of the deformation, I guess, but it is an inconsistency, I suppose.
But if it's linear, so does it really make a difference?
It's linear if you it's not exactly linear if the stiffness depends on the volume or on the wall
Yeah,
distance,
okay.
the wall
Yeah. Yeah, it's true. Yeah. So these are also some kind of inconsistencies we have to solve to make sure that it is really consistent. I think, yes. Yeah. Yeah, so the thing also with the mesh deformation is that we also want to move the mesh projection step, or to project your gradients, into the adjoint solver.
Yeah, and
Right.
it's because of that you said that you wanted to do that, that I raised this question, because if we want to fix this inconsistency, then it would be a bit more difficult. And the other downside of moving that projection into the joint solver completely is that SU2 dot currently has the capability of what does it let you do? It lets you specify the derivatives yourself without them coming from SU2, right? Something like that.
Yeah.
Yeah. Once upon a time, I put in an option just to read in an arbitrary volume file of sensitivities. So if you computed them from another source like Fluent or any other adjoint code on the same mesh, you could at least import them. Again, not consistent by any means, but it makes the tool more flexible. You can use it more plug and play with other systems.
Yeah. So yeah, that's another consideration if we want to, move the projection step into other areas, that if we want to keep this kind of functionality slash flexibility or not.
Yeah, but this is independent, right? Because this only is for the surface parameterization and not for the sensitivity.
No, it's for the volume. It's for the volume parameterization. So the SU2 dot lets you it lets you get the sensitivity from lets you get the volume sensitivities either from a solution file or from
okay, so they're read in before you do the derivative of the.
Yeah, that's right. Yeah.
Oh, okay, yeah. Okay. Yeah, okay.
I mean, I don't know who else using that feature. I mean, it's up for debate whether we want to keep it. But it's there. Yeah, you're correct. It's a simple ASCII file format. I think it's like XYZ sensitivities in a file. That's all.
Yeah. So the advantage of like having that in the adjoint server would be that at the moment it's very confusing, right? Because you get something out of the adjoint server, and then you have to do an additional step to actually get the sensitivities that you need, because the other ones are not used. You don't need them. So it's like a little bit confusing for users. This is what I think.
Yeah, I think it took me a while to figure out that you needed to project your adjoints onto to do the additional step to get the sensitivities that you actually want.
Yeah, exactly.
One historical comment on this: there's really no great reason for having SU2 dot separate with the discrete adjoint. The reason it was done separately a long time ago was that with the surface formulation of the continuous adjoint, you don't need volume sensitivities at all, or any mesh sensitivities. So it was as simple as just evaluating a little integral on the surface, and we used to read in a little CSV file. And so that's why we did it separately in SU2 dot. It was so simple and quick, it didn't matter. But once the discrete adjoint showed up and we need mesh sensitivities and et cetera, we never really reconsidered the design. So, but what I'm saying is there's no big reason to keep it the way it is.
Yeah. Because that would remove that step. I think that would maybe make it a little bit easier. I mean, the adjoint solver already works with the mesh deformation included. So you just have to enable it with an option, but it's already there and it works. Yeah, okay, but these are some things, that we can already do, incorporating that into the agent solver, because this just requires to disable that in the dot step, the mesh deformation differentiation essentially. Or is there some other things that you want to add, Pedro?
No, not really. I mean, off the top of my head, no, but it's something to consider. And on the design variable side, I agree with. I think that's, in terms of user input, that's the bit that I think needs more cleanup or needs more user friendliness. So right now, to set up some FFD deformation, you really need to sit down and look at the thing with 4 pairs of eyes almost, to make sure that
yeah, it should be more automatic essentially.
Yeah, and one point of this last thing that's on the bottom, requiring config structure, is the idea to try and get the config exposed to Python as well?
Well, that would be the ideal case, because then you could change something. You just evaluate the solver with a new config. It doesn't work. It probably will not work like that, because even upon construction, they use a lot of different things from the config and store it in their own scope. But it would be nice to do that and then create a solver based on that config. But with the current config structure, it's not possible, I think, because we have to expose every single function.
Yeah.
And that's, well, it's not, you don't have to do anything manual for exposing it, but they're also not, then we need also set functions for all the options and stuff like that. And it's not possible, I think, to maintain. But
may I add something here?
Yeah.
So I think exposing the config can be done easily with Swig. So Swig basically.
I know that you can. I mean, it's automatic. You can automatically expose all the functions from the config structure, but right now we don't have, for example, set functions for all the different options. And this is what you would need if you want to create a complete a config object completely in Python without going through a text file.
I see. Okay.
And that would be a huge thing, right? It's already very big, the class, and we need a lot more functions. I don't think that it is feasible at the moment with the current structure.
Tim, one thing I think we should consider is whether to finally move from a getter setter kind of a thing to maybe just a data struct for the config. Because I mean, we don't need that many methods. We could move all the methods out and just have direct access.
Yeah,
I would be more in favor of if we want to do that. I think it's a good idea, but we need to kind of group things a bit before, have kind of a hierarchy of configuration options, because if it's just a struct with all those fields and you can freely modify all of them, I don't know. I imagine a lot of bugs coming from that.
So yeah, exactly. So there needs to be some structure, maybe in some kind of a JSON thing or something like that, right? So and also
sort of a structure with the various convective numerical options or something in one branch of that, and then you sort of go more and more granular as you go down the tree.
Exactly.
Yes.
Yeah. Would
so,
be some kind of tree structure.
You can still have some high level get and set. So get linear solver options, and then the return of that would be some small struct that where you could clearly identify what is what and make it a bit more modular, because some things we probably don't want to. That would hopefully help decide what should be exposed to Python and what shouldn't, because I guess some settings would be static during an optimization.
Mm-hmm. Yeah. Yeah. So I mean, there are several approaches for the config structure, right? I mean, one option would also to generate the code for this config class from some more readable structure, because you can easily generate like code from, like, for example, from a JSON file, right? That would also help to interact maybe possibly with some graphical user interfaces and stuff like that. But yeah, I don't know what the best way would be. But it still requires a lot of work because we have to read everything. So already for the output, it was very complicated, but now the config, like everything depends on the config, right? So it will change like everything. And it's, I think that's very hard. So yeah, but if you have any great ideas, but it should be a separate topic, I think. It's a topic on its own.
Yeah, and it would be nice to have it. I think it would also increase the robustness of the Python in-memory scripts that we have, and even with the optimization, if you needed to change conditions, like it can be done through the config structure. Your multi-point optimizations and things like that get a lot easier to specify then. Yes. So it's definitely a good thing to aim towards eventually getting to.
Yeah. But yeah, I don't know how we can start that process, and because it's, I don't know.
Yeah, it's a tricky.
I think we should start from the end. And I think we should start with what do you want to write to run an optimization as a user?
Yeah.
So envision what the user experience would be to set up the optimization. Like, write Python code that doesn't work, let's say, and then we
so
and then we go down here from there.
So yeah. This is just a small example on how I would envision on how to evaluate a function and a gradient, right? So you create like a okay, you don't see my mouse pointer. You see it, right? So I thought, okay, you create just a solver based on, like it is in the C++ code actually at the moment. So you have a config option, you have a config object, you have a geometry object, and you create a direct solver out of that. Then you run the solver. So, well, possibly also with the config, but then you can just get like any history field that you want out of it. You can run the adjoint solver with any like objective function that you can think of, and you can just get the gradient in the end, right? That would be my idea on how something like that should look like. But okay, I've not shown here how to create a config or geometry, but you can imagine how it would look like. I don't know.
Yeah. So the other level of abstraction, or possibly the key level of abstraction here for the optimizations would be how the variables are manipulated. So in the tool I currently have, I have my lowest level abstractions are parameters and variables. And parameters are useful, for example, if you want to change some settings to have multiple operating points, or change some boundary conditions or whatever. And so that's something that you could, with the same solver, let's say, evaluate different functions just by changing parameters around the same variables, around the same design vector. And then once you have those variables, you can start doing some transformations on them on the Python side to make things more engineering like for the optimizer. So instead of just, you can start, the things we do with grouping some control points of the FFD to control, I don't know, camber or whatever. That's something that can, possibly be more easily done in Python than having to code all this functionality in C++ and then expose it to the configuration and so on.
Careful what we need to differentiate and what not, right? I mean, we can of course always use finite differences.
But some transformations are very simple. For example, if you just have like a translation variable, it's just, you just add everything or.
Yeah.
And all of the FFD is finite difference gradient calculation right now, and I don't know if there is a way to get an adjoint to get all sensitivities to FFD points.
Where the AD, if you run the discrete adjoint solver, it uses AD to compute the derivative.
Yeah.
Does it? Because whenever I'm running well, I guess. Oh, sorry. That's for any of the. Oh yeah, sorry. That was I misspoke. Any of the geometry evaluation.
Oh yeah, that's true.
All of that is done finite difference.
Yes, they are finite differences.
It's funny you should mention that. Yesterday or the day before, I was trying to make a SU2 GeoAD.
Mm-hmm.
And for some reason, it does not work.
Maybe it's more complicated to differentiate than the solver.
No, absolutely. I think it is. all those functions to the compute wing or whatever. I was just getting. It was not even garbage values. It was zero. All the gradients I was getting was 0, 0, 0, 0, 0.
Okay, maybe there's a double somewhere inside or something like that.
Yeah.
Maybe somewhere there changes. Like, I don't know. Yeah, but that means that all of these things should stay essentially, like the complex things should stay as C++, right?
The numerically heavy things.
Yeah.
Anything that requires like matrix inversions or linear solves probably should stay in.
Yeah, but the thing is also that even if you have some simple things that where the derivative, you still have to like use it in Python somehow to compute the derivative, right?
Yeah.
So it's still an additional step that you have there.
Yeah. You're right.
Yeah. That's why I'm always in favor of pushing as much as we can to like C++, because then it's like at least in some sense automatic.
Yeah.
Yeah. So, but we have to keep a balance between like having it like flexible and
and along with what Pedro was saying, we have to think about how we want to specify objective functions, constraints, and design variables. It's in the sort of way that you've done here with the workflow, but how to define an optimization, what the ideal situation is if. At the end of this, what do we want the optimization specification to look like?
Yeah. So then I would say we create like a mock-up script, like Pedro already said, like which is like in Python, but of course it doesn't work. But how it should look like?
Yeah, it's just like a skeleton.
Like a skeleton, yes. Also to see like how to define like you said, define the optimization problem, because it should maybe not be in the config file for the solver, right? You
Yeah.
want to define it somewhere in an external file or wherever.
I think it should be, if we go the Python way, the optimization formulation should be given entirely by how you prepare this script. So my suggestion there would be to have some optimization driver classes that interface with particular optimizers, and in this driver, the abstract interface is things like add function, and when you add a function to the driver, you assign it a role. So maybe you say that it's a minimization objective with a certain weight. Maybe you say it's a constraint with certain bounds. And then when you want to run the problem, you just take this driver and you can pass this driver to a particular optimizer, say the SciPy. So the driver then gives you small functionality to interface with the SciPy optimized function, or something that is compatible with that kind of signature, or something that is compatible with something else that has a Python interface, basically.
Yeah, I think that makes sense. Yeah, but I'm always also thinking about how the user defines the optimization problem, right? So that means what kind of objective function, how the design variables are specified and stuff like that. Because we don't want to have that in Python directly, right? Because I don't know, it's maybe not too user friendly, because not everybody is like familiar with Python, to be honest. Especially a lot of users that we have.
Yeah, well, yeah, that's the thing. If you try to make it completely automatic, I think we're gonna end up in a very similar. We will end up in a similar position in terms of the complexity of all the options that the framework eventually needs to handle. I don't know. I find it more intuitive to specify these things via Python, to say I want to minimize this or I want to maximize that, than to write that in a text file. I don't know.
Well, I mean, you can have like a skeleton, like you said, or like some basic optimization problems predefined for shape optimization or for aerodynamic shape optimization, and then you can just give it the objective function and like how your design variables look like in some text file, right? That's what I mean. So that for common optimization problems that you don't have to like deal with the Python code.
Yeah, well, I mean, yeah, if you have, we could have some templates or.
So there are some things that need to be rethought, like how FFD design variables are being specified, and I'm sure there's some better way to do that than what we have now, and to try and make it more user friendly. Whether that's a text file or a Python function, I'm not sure yet. I guess we need to just need to like try different mock-ups and see what people like and what people don't.
Yeah. Mm-hmm.
So should we try and make some we could like work independently a little bit and try and figure out what our ideal interface looks like, and then
if people can just, or if you and Pedro or can just define or just write down how you would imagine like it, and then we can start from there and like refine it.
Yeah, that's, I mean, I can definitely do that, and Pedro, we can talk about this if you want to, and if anyone else wants to chime in and has some skin in the game, then feel free to reach out to either of us and we can have a conversation.
Yeah, absolutely. Yeah, I like the idea of putting together this mock-ups or proposed workflows. Maybe we can create an issue or well, there's already a shape optimization issue.
Yeah.
We could maybe put some options there, and then
Yeah.
by next week, when we start the discussion, it will be around that.
Yeah.
Yeah, and then maybe create a Slack channel for everybody who wants to join on that effort. Yeah, I think that's a good way to start, because it's long overdue actually.
Yeah, and if we have something, if we have an idea what we want it to look like at the end, then at least we can work towards that. We can start working towards that with some sort of goal.
Yeah, exactly.
Yeah, because this kind of functionality, I think it would help bound the design of the Python wrapper to then support the functionality.
Yeah. And then finally, we can use all the capabilities of the H1 solver. It's really limited. It's used at the moment.
and especially with the expression language that you're putting in place, I think there's some really powerful stuff we can do. For example, if we have this weighted objectives, it's much more efficient to create if we have different objectives from the same direct evaluation, and we can combine them, you can create the combined objectives such that you only run one adjoint instead of running multiple adjoints and then combining the results after you run all of them. So
yeah, that's a good point.
Yeah, I wanted to get rid of all the special implementations that we have at the moment for this combination of objective functions, because it's a little bit crazy actually.
Oh yeah, Tim, I had a thing about that. Well, not about this, but about being able to use output structures, things from using the new output structure for things that are in SU2 Geo, or because there's a bunch of files that are output from some of these other modules that don't use the output structure but would benefit from using it. I don't know if there's a way to do that, because it seems like it is fairly ingrained in the like dependent on solver classes and things like that right now.
Yeah, it is, unfortunately.
Okay.
But what do you think of, for example?
So, for example, in this SU2 Geo is on the top of my head right now, but when it does like thickness evaluations or like makes cuts along the wing, it'll create files for the airfoil shapes or like all the other objective functions that are associated with it, like maximum thickness or thickness to chord ratio, etc. And it would be nice to be able to use some of the functionality of the output structure where you specify separate, like specific outputs from those functions as well. Although some of that might be mitigated if we move some of these things to Python anyway, but.
Okay. Yeah, I can think about something.
Well, because so some of the things are, I guess it's just like having a CSV writer where you can specify a header and a way to get that function.
Well, for that you can, for example, use the tabular printing toolbox. This table printer.
Okay.
For something like that, I think it's the easiest way to get like an output like that.
Okay, I'll look into the printing toolbox then.
Yeah. But maybe we need some more general output things. Yeah, that can also be used in other places.
Yeah.
Okay. So Are there any other things regarding the optimization framework?
No, not really. I think
We can give a good
we have kind of after an hour after another meeting, we have some ideas to go and do some prototyping.
Yeah, so we also have to talk at some point about how to expose the things. Because like I've written here, you can expose like all the classes that we already have, or you create special wrapper classes that only expose a subset of functions. That's also something we have to discuss, I guess. But we can do that at a later point if we have like maybe an idea on what we actually need.
Yeah. I mean, I like exposing the classes, but after we make them a lot lighter. So I think we have, far too many virtual methods in C solver, for example, that are not needed.
Yeah, I think we could, if we would go through the whole code and throw out all the virtual functions that we actually don't need, that would already help a lot, I think.
Yeah. That would make it a lot more manageable to then expose the entire class and.
Yeah. Okay. Okay, perfect. Then we are under 2 hours. That's good. If there's nothing else, then I would say for next week, we try to get some mock-ups and then we can start the discussion then from there, I would say.
Sounds good.
Yeah, sounds good.
Right. Thanks, guys.
Okay, then thanks a lot. And then we talk to each other next week at the same time.
Sounds good.
Perfect.
Okay.
Bye.
Okay.
Bye-bye.
Later,
Okay,
everybody.
bye.
Bye.
Yeah.
Bye.